Hello there, Mr. Sutton here, bringing you the final of the convergence tests, the limit comparison test. In this one, we'll be using this test, yes, you guessed it, to determine convergence. For your warm-up, pause the video and see if you can figure out the convergence or divergence of this series. Alright, so we've tried our litany of tests here. Nth term test isn't useful. Ratio test isn't really going to help us out here either. It's not a p-series, but it's pretty close. It's kind of like the harmonic, so we're going to try some direct comparison here because that's really all we've got. So let's compare it to 1 over n, which again is the harmonic series, and we know that that diverges. So putting these things in order, 2n plus 1, that's a larger denominator than n. That means that the original series is smaller than the harmonic series, so we can write 0 less than or equal to 1 over 2n plus 1, less than or equal to n, and then that's going to be true for n values 1 or greater. And this proves nothing. We have a series that is less than a diverging series. Well, less than diverging might mean converging, or might mean just diverging more slowly. So our series are in the wrong order for direct comparison to work. We need something else. When direct comparison isn't quite giving us the results we want, we can turn to limit comparison. The limit comparison test starts with two series that have positive nth terms, just like the direct comparison test, and we're going to take these terms and find the limit as n approaches infinity of the nth terms. So let's let L represent that limit. The limit as n approaches infinity of a over b. If that limit is between 0 and infinity, in other words, if it's just some finite number that's positive, any number will do, then we can conclude the following. This means that sigma A and sigma B either both converge or both diverge. If we know what one of these series is doing and we get a number between 0 and infinity, then we automatically know exactly what the other series is doing in terms of convergence or divergence. Now, as a little bit of a further translation on what's going on here, if the ratio of the nth terms is approaching some finite positive number, that tells us the two series are behaving in more or less the same way, so we can draw conclusions about convergence and divergence. Now, there is a couple caveats here. First off, A and B both have to be positive. Otherwise, this is going to mess up that whole between 0 and infinity kind of relationship, because then you can start getting negative things out of this. And the other thing, this is less of a caveat and more of a cool thing, is that since we just want any number between 0 and infinity, it actually doesn't matter which way we divide the nth terms. You might have been wondering, well, does it make a difference if I have A on top or B? It does not. If we get a finite number dividing A by B, like 2 over 1, dividing B by A would give us 1/2. It would give us some other finite positive number, and we're good to go. Now that we've learned a little bit about the limit comparison test, let's see it in action. So we're going to try out that warm-up series again. Now this is the one where direct comparison did not help us out. So if direct comparison is not going to work, we try limit comparison, which we start by picking and determining convergence for a comparison series. Well, we kind of already did that, right? We said the harmonic series was a good match for this. And since it is the harmonic, that series is going to diverge. Once you've got your comparison series picked out, you're next going to have to establish that both series are positive. And this is pretty easy to do. Just literally say they're both greater than 0. Just make sure you choose the right n values to make that true. So we can say this original series is greater than 0, the harmonic is greater than 0, and that's going to be true for n greater than or equal to 1. Okay, so once we've got that established, which was the conditions for limit comparison, we're going to take the limit of the ratio of our nth terms. So we're basically going to do original series over comparison series. So limit as n approaches infinity of 1 over 2n plus 1 over 1 over n. And this is kind of like the ratio test, only these are two completely different functions. You're not doing n plus 1th term or anything like that. So same change flip in this thing. We've got n in the numerator and 2n plus 1 in the denominator. As n goes to infinity, we can ignore this plus 1 now, so we just have n over 2n, which reduces to 1/2. The last bit of this is that we have to show that our limit that we just found, and notice that I said let L equal all this, so now I can refer to this just by L. We can show the limit is between 0 and infinity, so it's a positive number and it's a finite number, And then based off that, we'll state whether or not this limit converges. So we've got L. I'm just going to write 0 less than L less than infinity. And I write this every single time since I always write L equals whatever this limit is. Based on the fact that my limit is a finite positive number, since my original series or my comparison series diverged, I can conclude that this series also diverges by the limit comparison test. Here's another example. Pause the video and try this one out. All right, so if you tried nth term test and maybe thought about ratio test and then said no way, this leads us to the comparison tests. So we don't have to actually decide on a comparison test until we've got our comparison series. I'm going to use n to the third over n to the, 2, 3, 5, n to the fifth down there, which I can go ahead and reduce to 1 over n squared, which with either comparison test, I'm going to need to figure out if it converges or diverges. This is a p-series with a p-value of 2. Since that's greater than 1, this converges by the p-series test. So now we have to decide direct comparison or limit comparison. Well, direct comparison is going to work if the original series is less than this converging series that we just came up with. It looks like the denominator is certainly going to be bigger, so that would help us out. The numerator, on the other hand, I can't really conclusively show that this is always going to be less than 1. In fact, it probably is not going to be less than 1 as n gets larger and larger. So direct comparison is not going to work here. We're going to use limit comparison to be on the safe side. So again, establish that the original and the comparison series are greater than 0. So original is greater than 0. P-series here is greater than 0. And that's going to be true for n greater than or equal to 1. If you plug in 1 here, it works out. So next, I need my limit of the original series over the comparison series. So there's the original series. Here's the comparison series. Limit as n approaches infinity. And again, let's let all of this equal L, whatever it comes out to. Same change flip. If I multiply n squared by the numerator here, that's going to be 5n to the fifth minus 3n squared. We'll do that in a sec. And in the denominator, I just have this denominator here. So as n goes to infinity, I can forget about the lesser terms. Really, when the dust settles, I have a 5n to the fifth over an n to the fifth, which I can simplify if I wanted to just simply 5. Now, since this 5 is between 0 and infinity, that tells us that my original series is going to behave just like the comparison series, which means it's going to converge by the limit comparison test. Here's one more for you to try out. Pause the video and give it a shot. All right, so on this one, we can compare this to 2/3 to the n. Nothing else is really going to work except a comparison test here. 2/3 to the n, that's a geometric series. That has a common ratio of 2/3, and the absolute value of that is less than 1. So this converges. Now, are we going with limit or direct comparison for this one? Well, for this one, the denominator is going to be smaller, which means a larger overall number, which means that proving convergence by this is not going to work out. So again, we're going to limit comparison. So let me establish that this is greater than 0, and my comparison series is also greater than 0. And is this true for n greater than or equal to 1? Well, if I plug in 1 for n, I end up with 3 minus 5 in the denominator, which is no good. So I'm going to start with an n value of 2, just to ensure that I have positive numbers all the way through. So n greater than or equal to 2 on this one. And now we've got original function divided by comparison series, limit as n approaches infinity, equals L. So we've got original function, comparison series, same change flip. So we've got 2 to the n times 3 to the n in the numerator, and we have this 3 to the n minus 5 and 2 to the n in the denominator. 2 to the n's are going to cancel. And as n approaches infinity, we can actually forget about this negative 5 in here, and we can also cancel out the 3 to the n's. So this whole thing just comes out to 1. Since that is a number between 0 and infinity, we can say that this series up here is going to converge by limit comparison. And that one is going to wrap it up for convergence. Till next time, Mr. Sutton signing off.